Hey everyone, welcome back. And last time we looked at water and oil. We've actually been looking at water and oil for a couple of times now, and we saw that the oil and water didn't mix, and we're trying to figure out kind of why that is and what causes that. And some of the questions that I've been reading about from you all have been talking about what kinds of elements they are or about the charges that come from that. So for today's short experiment, what you're going to need is a little bit of oil and water. So I have cups of both here. And if you have some kind of eyedropper, that works really well. I have pipettes here. But if you don't have that, then don't worry. If you just have like a toothpick or something that you can use to dip into the water or the oil, you can try most of the experiment. And then you need a little bit of wax paper. So I have some wax paper here with oil and water labeled here, so you can see that. And what we're going to look at today is how the water and oil behave as drops. So what I'm going to do is I'm going to set up this right here. And if you look at the first thing we're going to look at is what kinds of how it comes out of the dropper and how well you can control it. Okay, so so this is kind of hard to see, but if you look at the water, so the water, if I take the water drop and I can make a pretty big drop, I can also control the drop pretty easily. So you can see that it gets pretty big. On the oil, it's a little harder to control. So this is the oil, and if I take the dropper, if it drops out, I can't suck it back up in here. If I take a little drop like this, it doesn't get quite as big, and as soon as it gets to a certain point, it just falls out, okay? So that's the first thing I want you to notice is how easily the things drop. The other thing I want you to notice is how they behave when you start spreading them out. So oil, if I take the oil and I start spreading it, you can see that it spreads out and it doesn't go back together. It just keeps spreading out, okay? If I try this with water now, let's see what happens with water. So the water is not spreading out, okay? You can see that it behaves a little differently. It sticks together. Looks like it's kind of, just stays as a drop and you just keep moving it around. So the question is, why does that happen? Why does the water stay as a drop and stick together? The oil kind of spreads out. What's causing that to happen? Some people were asking about what the elements have to do with the charges that are in the substance. So charge has a huge role in how these substances behave. And one of the things that we started looking at first semester was core charge. So let me just review a little bit about core charge. Core charge is, remember, the nucleus has protons and neutrons in it. So the protons are positive and neutrons don't really have a role. They're neutral. They take mass, but in this case, it doesn't really matter. But the positive charge pulls the outer electrons in. And so the core charge, we can figure out the core charge by looking at the group number of each element. So hydrogen, for instance, has core charge of 1. It's 1A. Something like carbon has a core charge of 4. So it's in 4A. Don't look at the top number. Oxygen has a core charge of 6. So the further down you go in the periodic table, the core charge increases, and that pulls the electrons in. Well, that also plays a role in something called electronegativity. So electronegativity is when something is bonded with something else. So if I have an element like oxygen and it is stuck to hydrogen, so it's forming a bond, and we'll talk more about bonds later, but when it's got a bond there, there's electrons involved in that bond. And the electrons can get pulled in either direction by elements, and that's determined by something called electronegativity. So electronegativity describes an atom's ability to attract bonding electrons toward itself. And so, for instance, if I have every element has an electronegativity value associated with it. It's a number. The highest number is fluorine right here. So that is 3.98. It's the highest. It pulls the electrons. When it's bonded with something, it pulls it really strongly. Something like francium down here, 0.7 is really low. It does not want to grab electrons at all because it's got a very low core charge. And so that's the lowest number. And some of these things here have no data because they don't really bond to anything. Helium doesn't bond to anything. Neon doesn't bond to anything. So really no data at all. So if I have two elements that have different electronegativities, the amount the electrons gets pulled in any direction depends on how big the numbers are and what the difference between those two numbers are. So if I have two elements here, like hydrogen on the left, with an electronegativity of 2.20, and fluorine on the right with electronegativity of 3.98, the electrons, if I take those two elements and subtract those numbers, if the difference is bigger than 0.5, we generally say that the bond is polar. That means the electrons are being pulled unevenly, or they're being shared unevenly between those two elements. So 3.98 subtract 2.20, the difference is 1.78. That means this set of electrons gets pulled towards the F. The fluorine now is pulling the electrons in this direction. And so because electrons have a negative charge, we say that this side of the molecule has a partial negative charge. And so this symbol here is the delta, lowercase d in Greek. So you don't have to worry about that, but it's lowercase delta, and we say this is partial negative charge because the electrons are being pulled in this direction. This is called a polar bond. So uneven sharing is a polar bond. Well, if this side is negative, well, that means that the other side has to balance it out. And so now this side takes a partial positive charge. So the hydrogen and fluorine, the electrons are unevenly pulled towards the F. This side here takes a negative charge. Well, this side takes a positive charge to balance that out. Okay, so this is a polar bond. If I have two elements and I have the numbers that are really close together, so the difference between them is less than 0.5. In this case, I have hydrogen, which is 2.20, iodine, which is 2.66. I subtract them, it's 0.46. That tells me that neither of these elements really is pulling much stronger on the electrons than the other. Iodine may be a little bit, but it's really not enough to get these electrons moving. And so in this case, we say that they are evenly shared. Evenly shared electrons lead to a non-polar bond. So there's no partial charges here. And this, now we say that this element, this compound is really kind of non-charged. So in the Google Doc, I have a couple of practice problems you can look at. I will give you the electronegativity values for a couple of different things here. And now we want to look at something like water. So water has two bonds in it. It has an H and an O here, and an O and an H here. And we actually don't want to combine anything. We're going to look at them separately. So one of the questions now is, why does water behave the way it does? And if we look at this bond here, we subtract those two numbers. What's the result of this bond? Is it polar or is it nonpolar? Same here. Is this bond polar or nonpolar? So we can look at that and see why does water behave the way it does? And then when we have something like oleic acid, which is in oil, there's a lot of bonds here. And so we can't look at all of these bonds. We kind of need to focus on what are the things that make up the bulk of the molecule. And so the bulk of the molecule is lots and lots of C's and H's. So we have tons and tons of C's and H's here. And if I look at the electronegativities of the C's and H's, so there's a couple O's here, but really if you look at how many there are compared to all the C's and H's, it's really not really substantial. So if carbon and hydrogen have electronegativities of 2.55 and 2.10, what does that tell us about how most of the electrons are shared in something like oleic acid or oil?